7.4 Using boundary conditions. You can use given boundary conditions to find a particular solution to a second-order differential equation. Since there are two arbitrary constants, you will need two boundary conditions to determine the complete particular solution. Example number 15. We have to find y in terms of x given that d squared y over dx squared minus y equals 2e to the x, and we've got boundary conditions dy over dx equals 0 and y equals 0 at x equals 0. Well, first thing we need to do is find the general solution. And for us to find the general solution, we first of all need to find the auxiliary equation, and to do this we need to set the right hand side equal to 0. So we've got the equation d squared y over dx squared minus y equals 0. So for the auxiliary equation, we've got m squared minus 1 equals 0, and therefore m is equal to plus minus 1. And therefore, what we can see from here then is that the homogeneous equation is equal to ae to the x plus be to the minus x. Now, for the particular integral, you'll notice over here we can't have y equals lambda e to the x, because over here we've got a term involving an e to the x. So what we do instead is we will multiply by x. So we have y equaling lambda x e to the x. And if we work out what dy over dx is, you'd find this to equal, through the product rule, lambda x e to the x plus lambda e to the x. And if we work out what d squared y over dx squared is, again through the product rule over here, we end up with lambda e to the x plus lambda x e to the x plus lambda e to the x, which we can simplify as lambda x e to the x plus 2 lambda e to the x. And what we will now do is substitute these back into here. So therefore, we've got lambda x e to the x plus 2 lambda e to the x minus lambda x e to the x. This is equal to 2e to the x. So therefore, hopefully here you can see we've got 2 lambda e to the x equaling 2 e to the x. Lambda is equal to 1. And knowing that lambda is equal to 1, we can therefore conclude for our particular integral we have y equals 1x times e to the x. And therefore, for the general solution, you'd find we have a e to the x plus b e to the minus x plus x e to the x. And now we need to use our boundary conditions. And first of all, you'll notice we've got this condition dy over dx equals 0 at x equals 0. So what we need to do now is differentiate this solution. So therefore, dy over dx, that's equal to, if we differentiate all this, a e to the x minus b e to the minus x, and here we need to use the product rule. So here we have e to the x plus xe to the x. And now substituting that condition, x equals 0, dy over dx equals 0, we have a to the e to the 0 minus be to the 0 plus e to the 0 plus 0 times by e to the 0 equals 0. Well, this term disappears, this term is 1. So what we are left with is a minus b equals minus 1. And we also have the other condition, x equals 0, y equals 0. So substituting it into here, we have a e to the 0 plus b e to the 0 plus 0 times by e to the 0 equals 0. So therefore, you can see here, we have a plus b equals 0. So if I call this equation 1 and this equation 2 and solve them simultaneously, you can see here a is equal to minus 1/2, b is equal to 1/2. And knowing the values of a and b, we can therefore conclude for the particular solution yps, that's equal to, if we substitute our known values of a and b back in here, we have minus 1/2 e to the x plus 1/2 e to the minus x plus x e to the x. This is the particular solution. Example number 16. Given that a particular integral is of the form lambda times by sine 2t, we have to find the solution to the differential equation d squared x over dt squared plus x equals 3 sine 2t, for which x equals 0 and dx over dt equals 1 when t equals 0. So to do this, we first of all need to find the auxiliary equation, and we do that by setting the right hand side equal to 0. So we've got d squared x over dt squared plus x equals 0, from which you can see the auxiliary equation. We've got m squared plus 1 equals 0. M is equal to plus minus I. And therefore, you can see here, we've got complex roots. So therefore, the homogeneous equation is equal to a times by cosine t plus b times by sine t. And for the particular integral, we will try x equals lambda times by sine 2t. We were told that in the question. So if we differentiate twice, we've got dx over dt equals 2 lambda cos 2t, and d squared x over dt squared is equal to minus 4 lambda times by sine 2t. So now if we substitute all of these into here, what we'll end up with is minus 4 lambda sine 2t plus lambda sine 2t equals 3 times sine 2t, from which we can see lambda is equal to minus 1. So therefore the particular integral is equal to minus sine 2t. And what we can do with this is state the general solution. That's equal to a times by the cosine of t plus b times by the sine of t minus sine 2t. And now we need to use our initial conditions. We know when t equals 0, x is equal to 0. So we've got 0 equals a times by 1 plus b times by 0 minus 0. A is equal to 0. And knowing that a is equal to 0, this term disappears. So therefore we've got the updated general solution, which is equal to b times by sine t minus sine 2t. And if we find out what dx over dt is, you can see dx over dt, that's equal to b times by cos t minus 2 times by cos 2t. And if we use the condition t equals 0, dx over dt equals 1, we've got b times by 1 minus 2 times by 1 equals 1. So we've got b minus 2 equals 1, b equals 3. So therefore the particular solution, xps, that's equal to, if we substitute back into here, we've got 3 times by the sine of t minus sine of 2t. This is our final answer.